An example of composition or cascade of two functions, as you can see, is shown here. We have input x going inside as input to the first function f of x, and then the intermediate result comes out of f of x and serve as the input to the second function in series or cascade g of x, and then after that is computed, we get the final output z, that is effectively g of f of x, which is referred to as g of f of x. So g of, and as you can see, input to g is the output from f, so it would be g of f of x, which nominally or symbolically we refer to it as g o f of x, which is referred to as composition of the two functions g and f in this format. Be careful that the order is very important. You cannot interchange the order of f and g. If you change it, f of g of x, which is the scenario if g comes first in the cascade and then f comes the second, would not be equal to what you see here, generally speaking. So the order of the two functions in cascade or composition matters a lot. You cannot just arbitrarily change the order. Okay, so we want to find this g of f of x as shown here. That's the target for this computation here. And how can we do that? Okay, the example is providing us with the definition of f of x. As you can see, x squared minus 1.5 is for this function, and also g of x, which is this function. So if we want to just in a brute force fashion compute the g o f of x as is shown here, then it means we need to compute g of f of x, which means we have to substitute for x inside the formula of g of x. Anywhere you see x, we need to substitute it with the f of x. So basically what I'm trying to say is x squared minus 1.5 needs to substitute x in these places. That would be a tedious computation, but that is the brute force method. But if you carefully take a look at how this g of x looks like, effectively you can see, let me change the color so that it's obvious, it's sort of more visible. Effectively you can see it's 2x and then plus 3 to the power 3. That is what is understandable here, because if you extend or if you expand this power of 3 of 2x plus 3, you can see it become 8x cubed plus 3 times the first component 2x raised to the power 2 times the second component plus 3 times the first component 2x times the second component to the power 2, and finally the second component to the power 3, which is 3 to the power 3, which is 27. Now we get the 27 matching this guy. We get 3 times 9 times 2, which becomes 54 times x. So we have this component as well, and 3 times 2 times 3 is 3 times 2 to the 2 times 3 is 36. So that is also there. So and x squared is also there. So effectively this component is 36x squared, and 8x cubed is 8x cubed. So if we do it this way, with this observation, then it's a much better and less tedious process. So what I'm going to do is then I am going to say, with this observation, I am going to say g o f of x as requested in this example is g of f of x, which means f comes first in the cascade as you can see, and g comes second as you can see. So now g of f of x is g of x squared minus 1.5. So I am going to substitute inside the formula for g of x, which is just one spot. Instead of x, I'm going to substitute x squared minus 1.5. So it becomes 2 times x squared minus 1.5 plus 3 to the power 3. So the nice thing is in this case become x squared minus 3 plus 3 to the power 3 and as a result become x to the power 6. Very interesting. So it made life much easier, that observation. GOF of x, which is g of f of x, is computed x to the power 6. And what is the nice observation about this function? Okay, so the overall function x to the power 6, I'm going to change the color so that it matches original color we did. So x to the, it didn't change. Okay, so x to the power 6. Effectively, that's a replacement for the overall function. So what I'm saying is, what I'm trying to say is, this overall function, GOF of x, is just x to the power 6. So you can replace this whole red box with x to the power 6. So x comes in to the red box, and effectively z equal to the final output. X to the power 6 goes out. That's the equivalent operation for the whole cascade or composition here. And of course, it's a function that is not necessarily one-to-one or not necessarily onto. It depends on what domain and codomain define for the function, because the look of it obviously is this look, that z, or the output, is something like this, and it's going up very fast. So let me use a different color so that it's clear what I'm showing. I'm just doing an extra work here in terms of showing you the function. When x equal to 0, y is z is 0. When x equal to 1, z is 1. And when x equal to negative 1, z is 1 as well. So, but if x is equal to 2, then z becomes 2 to the 6, quickly, exponentially exploding and increasing. 2 to the 6 is 64. So as soon as you go 2, then this thing goes and hit the let's say the curve of the function at z value of 64. So it's exponentially increasing on the z-axis or on vertical axis, and of course -2 as well. So as you can see that this function, if the domain is domain of all real number, then it's obviously not one-to-one, and it's obviously not onto if the codomain is real number, because this function can only cover z-value positive. Impossible for this function to service or cover negative z-values. So if you want this function to be both onto and one-to-one, then we need to define this function from r plus to r plus. So this is so if you define the function from r plus union 0 to, so basically 0 and all positive real numbers, r plus union 0, and the function is defined as GOF of x equal to x to the power 6. So if we define our function like this, then it is definitely an onto and one-to-one function as well. All right, so I am hopeful that this quick review of composition or cascade of functions, and in terms of just showing how it's computed and then potential ways to expedite the process of computation and reduce the tedious process if we can observe some sort of algebraic property like what we did, I hope that this is helpful.